In this video, we will take a look at reflections. And reflection is a type of transformation that works as follows. If a point P is not on a line M, the reflection image of P across line M is a point P prime, such that M is the perpendicular bisector of P prime. And I've drawn a quick sketch of that here. And the idea, of course, is that if it's sort of straight across and the same distance, you get the mirror image idea that we think of intuitively as having to do with reflections. And if P is on the line M, then it doesn't go anywhere, and the reflection image of a point is just the point itself. It's actually pretty easy to make a construction using a compass of a reflection across a line. You just need to make an arc that intersects, centered at the point that intersects the line of reflection twice. Then you need to go to those points of intersection and make additional arcs on the far side of M, so to speak. And they are going to intersect at a place that I will claim is P prime. And it's easy to demonstrate why that has to be the case, because the constant compass opening means that these lengths are all the same, and so we have a rhombus. And as we know, the diagonals of a rhombus are perpendicular, and the diagonals of any parallelogram, including a rhombus, have to bisect one another. We saw some time ago in a previous chapter that if you want to reflect a figure across the x-axis, what you need to do is just leave its x-coordinate alone and take the opposite of its y-coordinate. So A at 1, 1 will go to A prime at 1, negative 1. And it's pretty important to label these appropriately. B from 1, 4 will have its image at B prime at 1, negative 4. And C at 6, 4 will have its image at 6, negative 4. It will be C prime. And all of the points in between will sort of follow along in proportion to their relationships between A, B, and C. Now, there is, of course, a way of representing this transformation that we've seen previously. And it's a little arrow. And we wanted, as we said, to leave the x-coordinate alone and change the sign on the y-coordinate. There's actually a matrix that will accomplish this transformation, as we'll find is the case for many transformations. And the way that works is this. You imagine that you take some 2 by 2 matrix, you multiply by sort of a generic xy, and we would like to get a generic x opposite of y. And so what would that matrix have to be in order to accomplish that? Well, when I multiply this row across the x and the y, I have to get x, which means that's got to be a 1 and a 0, so that I take 1 times x and 0 times y, and I get x. And similarly, down here, I have to have a pair of numbers such that when I multiply by this column matrix, I get the opposite of y. And if I take 0 and negative 1, that's what will happen. So I'm going to say that that is a matrix for a reflection across the x-axis. And one notation for that is a lowercase r with a little subscript x. We can demonstrate how that works in the case of this figure by taking that matrix that I just derived. You don't have to worry so much about where these come from, but we are going to ask you to know some of them, and we'll give you others, and I'll give you more information about that. Now, I just put that to the left always of a 2 by whatever matrix that contains the coordinates of the figure. In this case, it's a 2 by 3, and so I have 1, 1, 1, 4. It's important to get these in order also, so that you sort of keep your wits about you. And then if I take the products, I have 1 plus 0, 1 plus 0, 6 plus 0, 0 plus negative 1, 0 plus negative 4, and 0 plus negative 4. And these are, in fact, the coordinates of my image. 1, negative 1, that was A prime. 1, negative 4, that was B prime. And 6, negative 4, that was C prime. Similarly, we can go across the y-axis. And it works in like fashion. In that case, what we did was to change the sign on the x-coordinate, leave the y-coordinate alone. So A would have its image A prime at negative 1, 1. Image of B would be B prime at negative 1, 4. And the image of C would be C prime at negative 6 polar. And you can, of course, accomplish that in terms of notation, or represent that in terms of notation, with just xy being sent to or mapped to opposite of x, y. In terms of matrices, if we wanted a matrix that would accomplish a reflection across the y-axis, it would have to be one that would take the point xy and turn it into the point opposite of x, y. And I'm going to claim it pretty much has to be this, because I need to be able to take this multiplication here and have the negative 1 change the sign and have the 0 sort of skip the y. So I got the opposite of x plus y. And then down in the second row we have 0 plus y. And I'll leave it to you to show that that fits the example, takes you to the right location. Going across y equals x, that was a little trickier. You may remember, you may not, that to go across y equals x, what you did was you reversed the positions of the x and y coordinates. So you don't change their signs, but you do swap the one for the other. And so, of course, that's not going to make too much difference to the point 1, 1. But the point 1, 4 will get mapped to the point 4, 1. So this is also A prime. B prime is going to be over here at 4, 1. And C prime is going to have to be then at 4, 6, which is roughly about here. And if I connect the dots, so to speak, I'm going to have something like that. And actually, what I probably should have done first thing is sketch in y equals x, but y equals x looks like so. And you can see the idea that this reflection image looks as though it's sort of the way it ought to look. Notice also that any point on the triangle that is on the line of reflection, this vertex and this sort of point midway between B and C, they don't go anywhere. If you want a matrix for that, a little trickier but still quite doable, you need to turn xy into yx. And the trick is, if I make that a 0, 1, then I have 0 times x and 1 times y, puts a y up there where I want it. And similarly, if I make that a 1, 0, that's going to take 1 times the x, 0 times the y, and stick it down below. If you're going across y equals the opposite of x, we saw back in the day that that goes to the opposite of y, opposite of x, and that line looks like this. And if you want a matrix, you can ask yourself what has to happen to xy in order to get you to opposite of y, opposite of x. Turns out this one will do the job, because if I do the multiplication, I'll get 0 plus the opposite of y in the first row, and I'll get the opposite of x plus y in the second row. You can also perform reflections back to back. And here's an example of that. If you reflect across, let's say, x equals 2, maybe a little bit trickier than an axis, but not so much. If I reflect this triangle across x equals 2, then this point T is not going to go anywhere. This point S, let's see, that's 4 units that way, so it's going to have to be 4 units this way. So I believe it's going to end up at something like -2. And R, let's see, that's, again, 4 to the right of this line, so its image is going to end up 4 to the left of this line. So let's see, that's S prime. This is going to be R prime. And we can make that reflection image in hopes that it looks like it's supposed to look. And you could then take that image and reflect it in turn across another line, and the line I've chosen in the example is y equals 1. So I need to reflect this point -2, 0 across y equals 1. So basically it needs to go from 1 below the line to 1 above the line. So there's my r double prime, -2, 1. Then this guy, -2, -2 is, let's see, 3 below the line. It's going to have to go to 3 above the line, which is going to be at 4. So here's S double prime at -2, 4. And finally, this T prime, which was the same as T, that is the point 2, -2. It's 3 below the line. It's got to go to 3 above the line. And so that's going to be something like 2, 4, and that's T double prime. And make a triangle. A little bit trickier question. What about reflecting a line across another line? What if we try to reflect the line y equals 2/3 x minus 1 across the line x equals 3? Well, you can do some things with slope, but probably the first thing we should do is to take note of the fact that since this point on this line is also on the line of reflection, it's not going to go anywhere. Now, we have this thing rising at the rate of 2/3. I'm going to say that it then has to, its reflection image then has to fall at the rate of 2/3, right? So I'm basically just charged with finding a line, and I'm not going to ask for the equation, but I'm just tasked with finding a line such that the slopes are opposites. And so that's not such a tough thing to do. One more thing that's kind of cool, and this has to do with finding the minimum distance when something is being bounced or reflected. Suppose I want to bounce a ball, let's say, from A to this wall over to B, or suppose I want to walk from one point to another, but I have to take in a point on some street in between. You might ask the question, well, where would I go to in order to minimize the total distance that I would have to travel? And the rather interesting answer is that if I just take the reflection image of A across this line, shoot a line back to B, that intersection there is going to identify for me the point that I want to head to if I want to minimize that distance. That concludes our set of examples on reflection.